Hey y'all. So yeah, I just watched my last video and like this lighting doesn't do anything good for me. I look dirty and gross and unshaven because quarantine's got me, you know, here existing. I'm sure you all know that. I miss you all so much. Um, Again, as always, please make sure you stop in this week to my office hours. I love getting to actually talk to you and hear your voices. So please come talk to me. I think it makes all of this so much easier to be able to uh, converse and discuss things and go over this together. Like I said, especially this week, that some of the stuff is really challenging. So please don't be hesitant to come to those office hours. It might seem weird at first, but I promise you, as soon as you do it, you're gonna be like, "Oh, that wasn't bad. That was actually really useful and really enjoyable." I'm sitting in there just helping people. So even if you just come lurk and watch other people get help, that could help you. So please come join me. You don't even have to turn your camera on. Like, you can just come there and talk. Okay, so this week we are on page 33. Coming over here. So page 33, we are talking about graphing the polar equations using the symmetry that we found in the last set of notes on page 32. So symmetry, like I said in the last example, kind of roughly, I think I batted around it for a minute and then didn't actually say it very clearly. But the importance about symmetry is because I can determine something as symmetrical, then what that tells me is I can just find the points on half the graph and use those points to replicate on the other side of the graph, making it less work. You could sit and plot every single point if you wanted to, but that would take forever. So we're going to look at how we can use symmetry to help us today. And I'm going to use some shortcuts today. Hopefully you've done that other homework assignment. If you didn't, do the other homework assignment. If you just watched page 32 and now you're watching page 33 and then you're going to watch page 34 and just move on with your life, I understand that. That's fine. But you're going to see that I take some shortcuts today that might not feel as comfortable for you yet, but will after you do that first homework assignment, or the first chunk of the homework assignment with practicing what's symmetrical and what's not symmetrical. So just be aware of that. With that, I'm going to jump right into it. Like, I've just got two examples. There really is nothing new for me to teach you other than just how to apply it. So you'll notice first that I did put a polar coordinate plane over there just because I think it'll look nicer if I can just graph it on that, because in my notes it looked real ugly. In fact, in my notes, like, I finally graphed, like, I did one graph with my own hand-drawn polar graph and then one without it because I was like, you can't even tell what I wrote. Okay, so we're going to talk about graphing this. I see this 4 sine of theta. Immediately what pops into my head is that I'm pretty certain that this is going to reflect over theta equals pi over 2. The reason that I'm really comfortable with saying that is anytime you see a sine equation, that's pretty much what happens. They're reflective over theta equals pi over 2. And your cosine equations are very commonly reflected over that polar axis. And we can just go ahead and test this just to be sure, right? We know that to test this, we're going to replace r with negative r and theta with negative theta. That came from last notes, that we to test over theta equals pi over 2, or the y-axis, we replace r and theta with negative signs. So I'm going to have negative r equals 4 sine of negative theta. Oop, I clicked. Oh, dang it. Hold on. Sorry. I clicked off of my pen. It's like all freaking out on me. Hello, computer. There we go. Okay, we're going to replace that was negative theta. Well, so the negative r stays, but over here what ends up happening is, well, we know that because sine of theta, or sine of negative theta is not equal to sine of theta, it's equal to, and we did this on those first notes, sine of negative theta is equal to negative sine of theta, because it's an odd function. So we're going to just change that. We're going to make this negative sine of theta, so ultimately it would be negative 4 sine of theta. Well, divide the negative r out, we get r equals, divide by negative 1, divide by negative 1, the negatives cancel. We get r equals 4 sine of theta, which looks exactly like the beginning one. So yes, this is symmetrical over the theta equals pi over 2. So clearing that off there for now. Like I said, I'll always put up my example at the end so you can look at it. What we need to do now is we've got to think about maybe some coordinates that we could go ahead and plug in here. Things that I could plug in and figure out what's going on in this graph. Now, because I know it's symmetrical along theta equals pi over 2, I don't have to go past pi over 2. So I'm going to kind of just pick some key coordinates from the first plane. So or from the first quadrant, essentially. Let's plug in 0 for my theta. And I should signify this is theta here. Let's plug in 0. Let's plug in pi over 6. My 30 degrees. Let's plug in pi over 3, my 60 degrees, and we can plug in pi over 2, my 90 degrees. I kind of skipped over the 45 there, to be honest with you. That's how they did it in the book, so that's kind of just what I'm doing. But you could plug in the pi over 4. It wouldn't make a difference. I just felt like after 4 points, I think that was enough information. So if we plug these things in, I'm going to come up to this original equation and just plug them in. So I'm going to plug in 0 for theta. So this becomes 4 sine of 0. And we'd solve this. Well, sine of 0, we know that at 0, sine of 0 is 0. So 0 times 4 would give me 0. So I know the radius here is 0. Same thing here. I'm going to plug in 4 sine and pi over 6. Well, I know that at 30 degrees, my sine is going to be 1/2. So this ends up being 4 times 1/2, which is 2. Over here, again, you can see the pattern. I'm taking 4 sine of theta and replacing theta with pi over 3. I know that at pi over 3, my sine is radical 3 over 2. Radical 3 over 2 times 4 is going to give me 4 radical 3 over 2, and the 4 divided by 2 divides to make 2. So I end up with 2 radical 3. And lastly, I know that at pi over 2, sine is equal to 1, and 1 times 4 is 4. There. So I have 4 polar coordinates there, and they're written backwards. We know it's supposed to be r theta, right? So I'm going to take this extra step here. And I would never expect you to necessarily do this, but let's just do it for the sake of practicing right now. I know that I have one coordinate at 0, 0. I have one coordinate at 2 pi over 6. Notice that I'm going up, like top to bottom. I have one that's at 2 radical 3. And hold on, that's not the right thing. Pi over 3. And I have 4 and pi over 2. So I'm going to graph those coordinates. So the first one's at 0, 0. So I go 0 on the radius, and then if it's 0 on the radius, well, that's pretty easy. I'm just going to leave it at 0, 0, the origin. My second one, I'm going to go out to the radius of 2. So I'm going to bring myself out 2 circles. So 1, 2. So right at this one. But then I'm going to move in the counterclockwise direction, pi over 6 units. So it looks like it's going to be right here. Boom. Next, I'm going to do 2 radical 3 and pi thirds. That could be a little bit hard. If you don't know your radicals easily, you may have to put that in your calculator. So if I want to put that in my calculator and see what decimal that was, I could do 2. Well, I would, if you have a graphing calculator, you can just put it straight in. But if you don't, you could take the square root of 3 and get that decimal, multiply it by 2, and ultimately you're going to get 2 point something, 2 point. I didn't do it. I just know it's slightly above 2, but not quite to 3. So I know that I'm going to go out slightly above 2 circles, just an estimate, somewhere in the middle. This doesn't have to be perfect. And I'm going to go up pi over 3. So 1, 2. So it's going to be like maybe here-ish. Okay. And my last one is going to be out 4 and then up pi over 2. So 1, 2, 3, 4, pi over 2. It's going to put me right about here. And you can see that what I have on this side is this circular shape. And it's not coming out very clear because I noticed as soon as I started doing it, this is ugly. That's not the correct, like, that's not a good polar graph. Hold on. Let's pull up a better one because I don't like that one. They didn't use radians there, but that's okay. We can make that work, right? Right. Just bear with me. Pretend it's in radians. It's good. Practicing converting between radians is smart anyways. There we go. Let's try plotting this again so it looks right. I should have paid more attention. I'm sorry. Okay. I'm going to quickly graph these then. So we had 0, 0, 2 pi over 6, a little above 2, and 60, and then 1, 2, 3, 4. Okay, so am I wrong? I think I'm wrong. I think I'm being stupid. I'm totally being stupid. 2 pi over 3, 2 radical 3 is like 3 point something. 3 square rooted. Don't do math in your heads, kid. It's 3.46. This point is not right. I should have gone out 1, 2, 3 and a half and then up to 60. Oh, that looks better. That looks way better. So you can see on this side what's happening is you've got this shape that's doing this. Woo! Well, since I know it's symmetrical over the line y equals 2, or sorry, theta equals 2. I keep wanting to say y. Theta equals pi over 2. I know that I could draw the other side of this too, which I'm just going to do in a different color just to signify. We would just do the same thing on the other side. Now, you can map it out if you want to. You can just reflect it over. See how this is at 30. So over on the 30 side, we put one here. Up here at my 60, I'd kind of just reflect that over to here. And then I already have my 0, my 90. So it's going to do that. And ultimately, you should end up with a circle. I know it's not the most pretty circle. Again, still learning how to write on this nicely. But let's come over here and look at it. So there you can go. You can see that my attempt here in the orange polar coordinates, I did this graph here, and then I just drew it without the polar lines on there to make it confusing. But it should look like that. All right, example 2. Again, if you need that, just pause it, read it, look over it, done. So example 2. Again, like I said, as you get better at these, you're going to start just looking at these things and recognizing, being like, oh, okay, this is cosine of theta. Cosine of theta tells me it's probably over the polar axis, if we're going to make a guess. So let me just test that again and plug it. And we know that to check polar axis, we leave the radius as is, but we plug in negative theta. And the reason I know that this isn't going to change is because I leave r the same, 1 minus 2 cosine of negative theta. Well, cosine of negative theta just gives us cosine of theta again, so it turns right back into what it was. Boom. Same thing. So I know that, yes, it is symmetrical over the polar axis. So ultimately, what I know, let's get rid of this one and put the other one in. What I know is at the end of this problem, when I come through here, whatever I have on my graph, I'm going to not do that. I'm going to reflect it right across that blue line that kind of got ugly at the end. But there, fixed it. Totally right. Okay. So with that, let's go ahead then and do the same thing. We're going to plug in some numbers to figure out what is going to work here. Okay, that one's not going away. I don't care. All right, so when I'm thinking about this, now this one's a little bit tougher. The other one, it was nice because we could just really worry about the first quadrant. Sometimes you may have to worry also a little bit about what's going on in the fourth quadrant when you're reflecting over the axis, but everything there was above the polar axis, so we didn't really have to worry about it. Here, I need to really worry about quadrant 1 and 2, so from all the way from 0 all the way up to pi. So the things that I'm going to plug in, I'm going to plug in for theta, 0. I'm going to plug in pi over 6. I'm going to plug in pi over 3, pi over 2. I'm going to plug in 2 pi over 3, 5 pi over 6, and pi. That's a lot more things to plug in. So just be mindful as we go through this. That's what we're plugging into that formula. I'm not going to write all those out because you saw it in the last one, right? So 0, the cosine of 0. Well, the cosine of 0 is going to be 1. 1 times negative 2 is negative 2. And then I have 1 minus 2, which is negative 1. So the radius here is negative 1. The cosine of pi over 6, going to use my hand tricks here, right? Put that down, radical 3 over 2. Well, radical 3 over 2 times negative 2 is going to be negative radical 3. So I end up with 1 minus radical 3. That's kind of ugly. We're going to not stress too much about that right now. Pi over 3. Okay, that's my 60. Put my finger down. That's going to be 1/2. 1/2 times negative 2 is negative 1. And 1 minus 1 is 0. So we're going to have a 0 there. Pi over 2, well, the cosine of pi over 2 is going to be 0. 0 times 2 is 0. So I have 1 minus 0, which is 1. 2 pi over 3, well, now we're moving over in that other quadrant. So it's still going to be, for my 2 pi over 3, I'm still going to have 1/2. And because it is going left this time, we're going into that quadrant on the left-hand side, the second quadrant, it's going to be negative 1/2. So negative 1/2 times 2, negative 2 is going to be positive 1, and 1 plus 1 is 2. 5 pi over 6, again, that's going to give me radical 3 over 2, but negative this time. So negative radical 3 over 2 times negative 2 is going to give me positive radical 3. And 1 plus radical 3, I'm just going to leave like that. And last is pi. Cosine of pi is going to give me negative 1. Negative 1 times negative 2 is positive 2, so 1 plus 2 is 3. If you need to write those down, please do. I know doing those in my head is maybe not the easiest thing yet, but with practice, you'll get there, and I just didn't want to clutter this up with a bunch of mess. But essentially, we just took all those things and plugged them in for theta here, solved this problem, and wrote down the radius. So make sure you can get those same answers. So we're just going to graph these going upwards now. So starting with this first one, we're going to go to a radius of negative 1, and then I'm going to move 0 degrees. So it's going to sit right here. This one, ooh, that's ugly, right? 1 minus radical 3. Let me not make the same mistake I made last time. Take out my calculator. 1 minus the square root of 3, and I get negative 0.73. So I know that it's going to be in between 1 and 2. So I'm like right here. And I'm going to pi over 6. Now we continue to move in the counterclockwise direction. So pi over 6 is going to be here, right? You're always moving this way for positive thetas. Whereas if it's a negative theta, then we can move that way on our graph. Okay, so then the next one is 0, pi over 3. Well, if it's at 0, then it doesn't matter. 0, 0. Let's go ahead and keep drawing this as we're going because I don't want to get too confused. Ultimately, so far, we've done this. You want to draw them in the order that you're graphing them in. So we've gone here, right? We've just made that little loop-de-loop. Okay, the next one is a radius of 1 and then pi over 2. So we're going to kind of continue just this looping pattern that's happening here. The next is we're going to graph 2 and 2 pi over 3. So 1, 2, out 2 pi over 3, which we know is 120 degrees. So we continue this little loop-de-loop. It's kind of like a spiral, right? It just keeps spiraling up here. It's getting kind of ugly. I'm trying my best. I'm doing my best. The next one, after we did that one, we're at 1 plus square root of 3. Again, let's do that. 1 plus 3 square rooted. I get 2.73. So let's go 1, 2, out a little bit more. And we're going to be at 5 pi over 6 for that. So over here at 150. So this is going to come this way. Okay, and then the last one is we're going to go over 3 and then out to pi. 1, 2, 3, and then all the way around to pi at 180 degrees. And so it wraps around like that. So now let's go ahead. Don't draw that line on your paper. It doesn't help. Okay, let's go ahead and reflect this, right? So we're reflecting over this blue line. So this one's going to stay the same. This point right here is going to reflect up to here. My 0, 0 is going to stay the same. This point's going to reflect downward to here. This point is going to reflect downward to here. Is that right? 1, 2, 1, 2. Yeah. This point is going to reflect downward to here. And then this point's going to stay here. So when I kind of connect this, you're going to see that it creates this. And I didn't quite go out as far over here like I probably should have just to make it match. But ultimately, those should look the same on the top and the bottom. But look at that. Look how cool that is. Like, we can graphically make that. Like, that equation, r equals 1 minus 2 cosine of theta, makes that really cool spiral shape. It's really fascinating to be able to graph these things. It's really cool to be able to come up with these. You can learn how to graph hearts by doing this. So you can make a heart appear in your graphing calculator. There it is, though, so you can see it a little bit more clearly. Like I said, my polar graphs are a little bit ugly in the orange there, so I drew it without the polar graph. It's a nice, beautiful little spiraled shape that we actually call a inside loop limison. We're going to talk about those names next week, though. We're not going to worry about them this week. But there you go. So that should get you through the entire first homework assignment completely, both parts of it. So try that first. Make sure you're comfortable with it. I would do that before you probably move on to the last part. So good luck with that. Let me know if you have any questions. Bye, everyone.